When we're talking about parallel circuits, it's helpful to then discuss Kirchhoff's current law. This is a good illustration of Kirchhoff's current law. It doesn't only apply to parallel elements, it actually applies to any circuit where you have branches in the circuit. So Kirchhoff's current law is similar to Kirchhoff's voltage law. Remember, the voltage law said that the voltage rises minus the voltage drops around a closed loop equals 0. Well, Kirchhoff's current law says that the sum of the currents entering a node or a junction of wires has to equal the currents leaving the node or the junction of wires. So let's look at how this is applied. So for our circuit here, we don't even know what's going on inside this blue area here. This is basically, it could be anything. It could be any circuit at all. We don't really care what's going on in there. But what we do know that is if we have 4 amps coming in over here and 8 amps coming in over here, that's 12. We have to have 12 amps leaving. So we've got 2 amps leaving this way and 10 leaving this way. So that makes sense. The current coming in has to equal the current leaving. It's just that simple. So think of it this way. If we had water running through a stream and then it faced a fork in the river or the stream, all of that water has to keep moving somewhere, but you'll have some of the water move this way and some this way, and it might depend on how narrow the stream is over here. The larger section would probably see the more water, or if it's more downhill than the other one. So basically, when we have 6 amps coming into a junction like this, some of the current will go this way and some will go this way. And it depends on what's going on those branches as to how much, right? And we'll see how to calculate that. So in this case, what do we have here? We have 5 amps coming in over on this left-hand side, coming into our junction at A. Now, some of that current is going to be going this way, some of it's going this way. So we're actually told that 4 amps of current are going down through R2. So what would the current be through I1? Well, that would be 5 amps minus 4, or 1. So we'd have to have 1 amp of current there through R1. Now, what happens at B? We have 1 amp of current coming in to B from this upper side, and we'd have to have that same 1 amp of current going down through R3. Now, this is the exact same current. The current through R1 has to continue through R3. Why? Because there's no other path for it to take. So R1 and R3, because of that, are in series. Okay, notice that's what that means. They have exactly the same current through one that's through the other. It has to continue through the other. And what about the current through this portion C down here? We've got 4 amps coming in this way, so we'd have to have 4 amps leaving. There's only one path for that to take. So actually R2 and R3, R2 and R4 are also in series. Okay, and then they come back together here, so we've got 1 amp this way and 4 amps coming in from R4, so this would make this our 5 amps back again. Okay, so it really didn't matter what path we took through there. That 5 amps split and then it came back together on the other side. And if you notice, if you're looking for parallel combinations here, if we combined R1 and R3 by adding them together, and we combined R2 and R4 by adding them together, we would have 2 parallel resistors there as well, but we'll get more into that later. So writing our KCL equations, that's what we have here. So let me get rid of what we've done up here. The equations are going to show us exactly the same thing. But if we write our equations, our Kirchhoff's current law equations, what they say is all the currents coming into the node minus the currents leaving the node or going out have to equal 0. Okay, so when we write our equation at node A, which is right here in our circuit, we have I coming in, so we're going to add that, minus I1 leaving, minus I2 leaving has to equal 0. Okay, so when we replace that I with 5, we don't know what I1 is, but I2 is 4 equals 0, then we can solve and find that I1 equals 1. And that's what we just talked through before, but we didn't actually write the equation to see that. The KCL at node B right here. So at node B, we have I1 coming in and I3 leaving. So I1 minus I3 would have to equal 0, which really just means that I3 is equal to I1, and they're both 1 amp. Same thing at C. It's exactly the same thing. The I2 has to equal I4, and they're both 4 amps there. And then at D right here, we see that we have I3 coming in, I4 coming in, and I5 leaving. So when I write my equation, I would say plus I3 plus I4 minus I5 must equal 0. When we plug in what we know, the 1 and the 4 ohms, 4 amps there coming in, it's pretty easy to find the current leaving the node on that side. Okay, so let's talk about what's going on here. Again, Kirchhoff's current law at node A. We have I1 coming in, so we're going to add that. I2 up here looks like it's coming in as well, so I'm going to add that in my equation. And then I3 is, we've drawn it as leaving, so we're assuming it's leaving the node. So I'm going to subtract that in my equation, and that has to equal 0 because at A, those are the only 3 currents that we see there. So if we do some solving there, we find that we must have 7 amps here. I3 would be 7 amps. Okay, so now let's look at B. KCL at node B. We have our 7 amps coming in, that's I3. I4 and I5, we're assuming they're both leaving the node. So we're going to subtract both of those in our KCL equation and set that equal to 0. So we know that I4 is 1 amp. So if we have, of our 7 amps coming in, 1 amp is leaving through R4, then that leaves 6 amps here. Okay, let's look at another example. I'm just going to kind of talk through this. We've got our 5 milliamps coming into our node right here. If 3.5 milliamps goes this way, what does that leave for here? 1.5 milliamps. They come back together on this side, so we have 1.5 milliamps coming in this way and 3.5 milliamps coming in this way. So I4 would just be our 5 milliamps again right here. We've got 5 milliamps coming in, 8 milliamps leaving this way. So we must have another 3 coming in from this direction, or KCL wouldn't work, right? We have to, if we have 8 milliamps leaving, we need a total of 8 milliamps coming into that node. So back up a little bit further, and if we know that we have 1 milliamp coming in from this direction, we would have to have another 2 milliamps coming in from I3. So what's going on over here? Well, that same 2 milliamps is leaving, the 1 milliamp is leaving, so I1 must be 3 milliamps as well, and that is I sub x. Okay, how about this next one? Now this is a little bit tricky because notice if we start at the top like we did last time, we don't know I2 or I3. So really that's going to be difficult for us to solve. However, if we look over here at this node on the right, we know 2 out of the 3 currents there. We know that we have 1.5 microamps leaving this way and 0.5 microamp leaving this way. So if that's the case, what do we have to have coming in? 2 microamps. And that's I3 right there. Now that helps us with, we can go back to the top node here. So now we know that we have 6 microamps coming in from the top and 2 microamps leaving through I3. So that means this must be 4 microamps. Sorry, I drew that as milli. It should be microamps. So we've got 4 microamps there. If we look right here, we've got 4 microamps coming in and 1.5 microamps coming in. So I4 must be 5.5 microamps. And then at the bottom here, we have 5.5 microamps coming in from I4 and the other 0.5 microamp here. So there's our 6 microamps. So notice the 6 microamps coming in went through all kinds of different directions. And what happened? 6 microamps came out on the bottom again. Okay, so let's apply this here, okay? Here we don't know our source voltage. Well, these are the calculations. We'll get to those in a minute. But we don't know the source voltage here. However, we do know the current coming from the source is 12.3 amperes. We know the current down here just in this portion of our wire is 10.8, okay? So just in that place right there. So what does that really tell us? Well, it tells us that the current through R2 and the current through R3 equal that 10.8. Now, why that's important is because that would be the same current up here, right? That current is going to split between R2 and R3, so it's also going to be 10.8 amperes up here. So the current coming in this way will be the current leaving this way. Okay, it's going to split between the R2 and R3 and it's going to come back together at the bottom again. So that's important because when we look right here in our circuit, we see that we have 12.3 amps coming in and 10.8 amps leaving. So that means that the other 1.5 amps would be right here. Okay, so it's also important to note that the 10.8 amps here, if we were to combine R2 and R3, this would be the current through the combination of the 20 and the 4. So that's what we've done here. We've combined just the 20 and the 4. And so if I were to redraw my circuit, I'll do that really quick over here, and I have that unknown R1 right here, then this would be my 3.33 ohm resistance over here that would have the 10.8 amps through it. Now that's important because if I multiply the 10.8 times the 3.33 as we did here, we will find the voltage drop to be 36 volts right here. Now that 36 volts is across what? It's across two parallel resistors. So the voltage drop across both of those resistors would also be 36 volts. And that's helpful because it's going to help us determine our current through each branch, right? So the current I3 would be V3 over R3, which is 36 volts over 4 ohms, or about 9 amps of current there. And the current through R2, I2 would be V2 over R2, 36 volts over 20 ohms, or I guess 1.8 amperes there. And I'm just going to plug that in and check. 36 divided by 20, it's 1.8. All right, so we know I3. We have figured out I3. Now E is just going to be my 36 volts, right? Because the voltage source is in parallel with R1, R2, and R3. So I must have 36 volts across there and also across R1 right here. All right, so what do I do next? Let's find R1. Ohm's law says R1 is going to be V1 over I1. I just figured out that I've got 36 volts across R1, and I must have 1.5 amperes through there. So that means that must be 24 ohms. Now, I found everything out, but I think what I want to do is to check. Remember, with our circuit analysis, we can check these answers fairly easily. So now that I know all my resistor values, and this is where we're going to check our values, how do we find RT again? Remember, that's 1 over 24 plus 1 over 20 plus 1 over 4. And my RT should be what? It should be around how much? Well, it should be less than 4, so that's what we're looking for, is something that's less than 4. And I get 2.93 ohms, which is actually less than 4, so we're good there. And now let's find our source current. If RT is 2.93, if I take my 36 volts and I divide by 2.93 ohms, I get 12.3 amperes. And notice that's what we were given in the beginning. So if you work through all of this and you know all of your voltages and all of your currents, Kirchhoff's current law is upheld for all of them, then at that point you know that you're probably right. And that's one of the real good benefits of having all of these tools in our toolbox, is that we can check behind and make sure everything is right. Okay, so one more problem here is we demonstrate Kirchhoff's current law, where we have 4 parallel resistors that should all have the same voltage across them, right? So the same voltage across, and we're going to figure out what that is. So let's go ahead and calculate that. How do we do that? Well, what we do is we look for a resistor where we know the resistor value and the current through that resistor, because we can calculate the voltage there. So if we call that R1, V1 is equal to I1 times R1. So we've got 6 amps of current through a 4 ohm resistor. So Ohm's law says that that has to be 24 volts. Okay, no choice, has to be 24 volts there, which is also my voltage across each parallel resistor. Now, just to remind you, how do we know all of these are in parallel? Well, if we look at what they're connected to on one side, okay, and then we look at what they're connected to on the other side, we see that each of these resistors has an orange side and each has a green side, so they're all in parallel. We know because they have 2 points in common. That's the definition. So if we want I2, that's going to be V2 over R2, where we've got 24 volts over 12 ohms, or 2 amps of current through there, 2 amps here, And then I3 would be V3 over R3. Again, 24 volts across that resistor, which is a 2 ohm resistor. So we've got 12 amps there. And then I4, where we've got 24 volts across a 40 ohm resistor. Which is 0.6 amperes or 600 milliamperes. So 0.6 amperes. So what's our total current? Well, there's a couple ways of figuring this out. But first, let's use Kirchhoff's current law to do that. So IT should equal I1 plus I2 plus I3 plus I4, because I1, 2, 3, and 4 are all leaving this orange node, and IT is coming in. So what would that be? 6 plus 2 is 8, plus 12 is 20, plus 0.6. I2 should be 20.6 amperes. And of course that should be the current leaving over here too, right? There's another way to check, right? Since we know all of our resistor values, and I'm going to come over here and we're going to check this. Let's find RT. So RT, 1 over 4 plus 1 over 12 plus 1 over 2 plus 1 over 40. And I'm going to do this with you, so pull out your calculator and work through this. Oops. Okay, so RT I get is 1.17, and that makes sense because our smallest resistor is 2 ohms, so it should be less than 2 ohms. And if our voltage supply is 24, or voltage across all of the branches is 24, that means our total current coming in should be 24 volts divided by the 1.17 ohm. And it looks like 20.6 amperes is what we found. So we did this a couple ways and checked ourselves at the end, and that looks like that worked. So review your Kirchhoff's current law, and we'll be using it a lot this semester.